Welcome to the Representation Theory module. This is a basic core module that will later be used by courses such as digital imaging processing, as well as a course that looks at the time series analysis of pulsar data. How we represent data in the world has an important impact on how we act, what we can learn about it. For example, look at this iris. The original image is given below, and these other images are transforms of that original image. In this one over here on the bottom left and on the top right, I've simply got a grayscale image. This one is a thresholded images where I represented in only two colors, black and white. Here I've reduced the number of colors, and here I've taken the color inverse. And finally, we can do artistic things as well as make it look like an impressionist painting. How you represent the data that you took the image of often allows you to highlight certain aspects of the image itself. For example, if all you were interested in how the veins of the iris looked within the flower, one of these grayscale images actually captures that feature to a much greater extent than the original color image. However, if you're interested in the chromatic colors, you would want a color image and sometimes even the negative color image to highlight certain aspects. We often make abstractions of the physical world digitally, and what this module does is it simply explores the basic mathematics of how you represent, store, and manipulate this data efficiently, and so doing to facilitate the extraction of useful information about the object being studied. The particular techniques that will be looked at in this lecture or the Fourier series and Fourier analysis, as well as some of the convergence properties. So to see where these techniques would be used, for example, one way of using it is in any one-dimensional data stream. We typically have a function g of t, where t is a discrete temporal coordinate, and g often is the recorded voltage of a measurement device. Or, for example, either the pulsar data that we look at over here, this is basically the voltage measured on a radio telescope that changes in time. Another very commonly used 1D data stream is an audio signal. For example, the audio that is mixed into this video is simply this discrete function where the amplitude is recorded at certain discrete time steps. Another example where this theory that we'll be exploring is very applicable is if we store data as a 2D dimensional function dependent on, say, x and y, where these are discrete spatial coordinates. And the classical example is either an image, a grayscale image photograph, or the output of medical devices that take x-rays, or, for example, any other thing that will give you a two-dimensional image or something in any frequency regime. Okay, typically what is stored in these two-dimensional functions is the amplitude at each pair of coordinates. In other words, for example, here where the pixels are dark, it has, say, for example, a low value. Where the pixels are white, it has a value of 1, and all the grayscales in between has in-between values. Okay. The amplitude of f at each of these coordinates is basically called for the images, the intensity or the grayscale of the image at that point. And the text that we'll be using, or in the case of if you're not doing, is this book on digital image processing by Gonzalez and Woods. There are a number of editions available. It doesn't matter too much what edition you could get, or a number of notes that are available on the website mentioned over here that were originally developed from this book. For this first module, we will be looking at the Fourier analysis and the Fourier series. The notes on the website suffice. However, there's some very useful examples in the digital image processing book. So even if you're going to be doing and looking at the pulsar data later on, this introduction to this first part is a really, really well written part of the book. Okay, I'm Jean de Brink, the voice you hear behind the video, and my physical location is in the Mathematical Science Building 109, and if you want to contact me, here's my email address. So this is still subject to change depending on the other lectures, but the provisional lectures and consultation hours. Initially for this part of the module, there will be 2 lectures of about, I will not be using the full 2 hours, of an hour and a half each. They'll take place in this venue, WWG 119, and on a Tuesday and a Wednesday. And should you want to see me privately or ask questions, you're encouraged to do it in class, but immediately after class, you are welcome to come to my office as well. Okay, so as I said, this particular lecture is just going to be an introduction to Fourier analysis. And Fourier analysis as applied to discrete images or discrete data, I will not get to during this lecture. I'm first going to give you a history of how it developed, because Fourier analysis actually developed from an analysis of continuum functions, and then later we'll derive the discrete transform that we actually use nowadays on computers for images. So a brief history of the Fourier series, which formed the foundation of the Fourier analysis used in digital image processing, is that it was first introduced by Joseph Fourier in 1822, and he introduced the idea of a Fourier series to try and find solutions to the heat equation, which is a partial differential equation. And he was one of the first people to solve this type of problem for a rod successfully. However, as any new technique, there were a number of rough edges, and then which interested a number of other people. And then another mathematician, Dirichlet, went on, and in 1829 he gave the conditions for functions that actually had a convergent Fourier series. So Fourier just went ahead and did something and got an answer. And then Dirichlet was a lot more rigorous, saying when you could actually do what Fourier did. And we'll discuss some of that as we go through the examples. And then finally, an important thing, this is not the final word in transforms. The theory was later generalized by Sturmlievel, that looked at a whole bunch of other orthogonal functions that are related with second-order ODEs. And while we'll not get to that in great detail in this course, it's useful at least to know how this theory was generalized. Just another fact of history is that Fourier series analysis is also known as harmonic analysis, and as we go on and look at the examples, the reason for this will become apparent, because we actually start looking at the tone content in some sense of the function. And then just a historic point, harmonic analysis comes from the word harmonicus, or the Greek word harmonicus, which basically means skilled in music, because it actually is a method that allows you to extract the various frequencies that constitute a function. Okay, so let's now go ahead and formally define what a Fourier series is. So a Fourier series of a function f of x, so for example anything, this blue line, that has been restricted to a defined interval. In other words, you want a function that's defined only on a small interval with length L, so minus L over 2 to L over 2. In other words, you only care about the function in this region. Okay, then we say the Fourier series is an approximating series that we denote tilde f. Okay, and it is made up of a linear combination of a set of basis functions. And in the case of Fourier, the basis functions have a particular form. In other words, the basis functions, which we call phi n of x, is simply the exponent times 2 pi I n x over L, where n is an integer. Okay, so it's a whole bunch, and these are complex functions, of functions with increasing number of oscillations that make the basis or the Fourier basis. And now the Fourier series is simply defined as a linear combination. In other words, these Cn's are constants of these basis functions. And typically you begin with n equals to 0. In other words, that's just a constant function. N equals to 1, that's a solely oscillating function. And you sum all the way to n equals to infinity. And these Cn's are then chosen so that they accurately approximate the original function. Okay, so just substituting in this particular case of what the basis functions are, we have that we could express the Fourier series of a function f in the following manner, where Cn's are constants. We will tell you how to choose in a moment. And they are called the Fourier coefficients. Now, these basis functions have a number of properties that make them exceedingly useful, and that Stumleyville actually went on later and generalized to make other transforms. So these basic properties that we can observe for these basis functions is that, firstly, the basis functions are periodic in L. And to see that basically means that phi n of x plus L is simply equals to phi n of x. And you should go and verify that on your own, and it's very easy to do. You simply work out what phi n of x plus L is, and you simplify it, and then you can actually show directly analytically that it is simply phi n of x. So that's the one property that the basis function has. The second property is that they are orthogonal on the domain minus L over 2 to L over 2. And by what I mean by orthogonal is that the integral from minus L over 2 to L over 2 of phi n multiplied by its complex conjugate phi k is equals to L times the delta function of nk. And just a reminder of what this thing means, this delta function nk, or this basically is 0 if n is not equals to k, and it is 1 if n is equals to k. So let's just take the example. If n is equals to k, you have that phi n of x is simply this thing, and phi n bar of x is simply that, the complex conjugate of that thing. If you multiply the two together, you get 1, and therefore the integral from minus L over 2 to L over 2 of 1 is simply L. Okay. If n is not equals to k, what you are finally left with is a complex oscillating function, which on average is 0. Once again, substitute the definition of phi n k in here and simply verify it for yourself. Now, these properties of the basis functions actually have a very strenuous implication for this Fourier series that is approximating the original function. In fact, we find that the Fourier series doesn't only approximate the original function, but it does more than that. So let's explore what these properties of the basis functions mean for the series we are using. So just a reminder up here on the slide, here are our basis functions. By definition, for the Fourier series, phi n is the complex function e to the 2 pi I n x over L, where n is an element of the integers. And this first property, phi n of x plus L equals to phi n of x, basically implies that the Fourier series also has that property. In other words, the Fourier series is made up of a linear combination of these functions, and because every single one has the property that it's periodic in L, therefore the series, which is simply the sum of it, can also be shown to be periodic in L. Okay, and what that means is that if the Fourier series approximates not just f, the original function, but the periodic continuation p of x of the function f of x on the interval minus L over 2 to L over 2. So let's see what that actually means graphically. So suppose you had your original function over here, okay, defined just on the interval where we care about. This periodic continuation p of x is basically has this property that is equals to f in this original interval, but outside this interval it also actually has a value, and it is simply, the periodic continuation is simply equals to this function but moved by a distance L in this direction, so that thing, and then it's the function itself over there as well as the function over there. So p of x is of the periodic continuation p of x associated with f of x is simply the original function, but that now obeys this property that it has period L. Okay, so that is our periodic continuation of f of x. Okay, so the Fourier series approximates not only the function, but it is defined away from this basic interval on which the function is defined, and it's simply periodically repeated, or it's a periodic continuation of the function. So that's property 1. Property 2 is actually very powerful in that it allows us to calculate the Fourier coefficients itself. In other words, the coefficients that help us make this approximation of the function is calculated by this orthogonality property P2. And to see how we do that, let us consider this integral. We take the original function, f of x, we multiply it by the complex conjugate of one of these basis functions phi of k. Okay, if the Fourier series of this function is a convergent, and this I'll get back to in time, we're just going to take Fourier's approach and solve the problem for now. If this function has a Fourier X series, we can replace this function with a Fourier series, just the definition of the Fourier series, where these are the Fourier coefficients, these are the basis functions, and then we are multiplying it with a complex conjugate of the basis function, and then we integrate from minus L over 2 to L over 2. Now the argument goes, if the sum in blue, in other words, the Fourier series converges, and I have not given the conditions for convergence yet, but if it converges, what we then can do is we can change the order of summation and integration. In other words, we can take the sum, move it outside the integral sign, and then reorder our calculation to try and simplify it. So if the sum converges, then we simply move this thing out. So we have Cn times everything that depends on x still has to be inside the integral. So it is the integral minus L over 2 to L over 2 of phi nx times the complex conjugate times dx. But we know from the orthogonality property of the basis functions that everything here in the bracket, in other words, we're going to use P2 as given on the previous page, everything here in the bracket is simply equals to L times this delta function of n and k. Okay, so we know what this integral is. It's simply L times this thing. And we know that delta nk is simply 0 if n is not equals to k. In other words, so everywhere where n is not equals to k, this whole sum collapses. Only when n is equals to k is this delta function equals to 1. And so we're left with the fact that this whole sum simply becomes L times ck. And what that means is if we have, in fact, obtained an expression for ck. Okay, so we now have used the orthogonality property to get an expression for ck, which is simply 1 over L times the integral of the function to which we're trying to get the Fourier approximation times the complex conjugate of the basis function times dx. And this is immensely powerful because it simply gives us a very direct way of calculating what these coefficients are. And I'll illustrate this in an example on the next slide. Okay, so just to write this thing, to process it a little bit more, the integral we have to compute to get ck is simply 1 over L over the domain where we've defined f times e to the minus 2 pi I nx over L. Right, so let us now look at an example. Let us say we want to find the Fourier transform. In other words, we want to find the linear approximation or the linear expansion of f using these basis functions that are just the exponential functions in the complex plane for a particular function which is just the absolute value of x. So let us now actually do that. The first step I always do is I draw the function because it can help me with a calculation, in fact. So let's consider the function or draw the function that we want to find the Fourier transform of, or the Fourier series of. So here it is f of x, simply the absolute value. We only care of f of x in the domain minus 1 to 1, so minus 1 to 1. So our L for this problem is 2. Okay. What we now want to do is we want to go about and we want to compute the Fourier coefficients, in other words, Cn, that we use to construct the series. And the way we compute it, we just derived in the previous slide, is we need the complex conjugate of the basis functions. So for this particular example with L equals to 2, we have that phi bar n is simply e to the minus pi I n x. Okay, and then we can use Euler's formula to be able to allow us to do the integrals, and we split this basis function into the real part, which is just cos n pi x, and because it's minus I sine n pi x over here. And so we're now going to use the orthogonality property that we derived on the previous slide to compute our Fourier coefficients. So there we have Cn is simply this integral. This is still the general case. And in our specific case, we are then going to say find Cn is equals to 1 over 2, so 1 over L, which is equals to 1 over 2. The integral from minus 1 to 1, the function f of x, which is just the absolute value of x, times cos n pi x minus I sine n pi x. So take note, these Fourier coefficients in general are complex numbers. They have both a real part that you can get by integrating this integral and an imaginary part that you can get by integrating the second integral. And this is true for any function you may choose. It might not be the absolute value function. So to make the integration as simple as possible, let's at first examine the symmetries. And so the absolute value of x in this case is even. Oh, sorry, the function, the absolute value of x is even. In other words, if you replace x with minus x, the value doesn't change. Cos is also an even function of x. However, sine is an odd function of x. And because we're integrating from minus 1 to 1, even function times an odd function will give you an odd function, and therefore the integral will be 0. And so all the imaginary integrals vanish, and we're left only with the even function times the even function, which is an even integral that we have to examine. Okay, so we are left with this integral. Also have a look at the domain. If we have an even function, we integrate it from minus 1 to 1, the value is equals to simply twice, in other words, twice the integral from 0 to 1. So there's been another step of simplification here, simply because we know we're integrating an even function. Okay, the next step in getting these quantities is to actually evaluate this integral, and to evaluate this integral, we integrate by parts. Okay, so here we have basically the integral of cos times, which is sine n pi x over n pi, evaluated times x, evaluated on the boundary between 0 and 1, and the second part is simply 1 over n pi times the integral from 0 to 1 of sine n pi x. Okay, this first integral, if we examine it, we can see when x is equals to 1, sine of n pi is always equals to 0. If x is equals to 0, that thing cancels it, so this first thing has 0 contribution. The second integral we can once again do analytically, and what that is simply minus 1 over n pi over here times minus the integral of that thing is minus 1 over n pi cos n pi x evaluated at the boundary between 0 and 1, and the value of cos n pi is simply equals to minus 1, okay, to the power n, and the value of cos at 0 is simply equals to 1, but it's subtracted because it's the lower bound, and these two multiply out to be 1 over n squared pi squared. So we have in effect computed our Fourier coefficients for this particular example. They're given by this formula. Just one thing that you have to be careful with is that check here when n is equals to 0, clearly this formula is infinite, which is not the case. The thing is, when n is equals to 0, you could not do the integration by parts. So if n is equals to 0, you're simply evaluating the integral of a half times the integral times the absolute value of x. So you're trying to find the value of the area underneath this graph times a half, which is effectively a half. Okay, So that's a special case when n is equals to 0. When n is even, in other words, then you're going to have that minus 1 to the n is just 1, minus 1, so you're going to have that it is always 0 if n is not equal to 0. And if n is odd, then you're going to have a non-zero value, so then you're going to have minus 2 over n squared pi squared. And one way of expressing the fact that n is odd is simply to put n equals to 2k plus 1, where k is an integer. Okay, and if you then go and you substitute these cn's into this original expression, then you can split it into n equals to 0, which is just the half. You can split the sum into the case where n equals to 0 and where n equals to positive, the positive series, and you can add it to the case where the n is equal to the negative series, and you can simplify it to prove that basically your Fourier series can now be written as a half minus 4 over pi squared, summing over k from 0 to infinity, times cos 2k plus 1 times pi x over 2k plus 1 squared. Just to note, this is a slightly different method from what is the way the solution is found in Christian's notes. It's good to compare the two approaches and to choose the one you are most comfortable to work things out on your own with. So look at the different approaches and see which one you find the easiest. But they are both valid. Okay, so let us now have a look at what we have actually done. We have started with this function, the absolute value function f of x. If we include only the terms up to n, or where the absolute value n is 0, all the approximation of f of x that we have, in other words, we look only at this term, is this a half. So the first term is in some sense always the average value of the function itself. So let's now go and add one more term. Let us take the case where k is equals to 1, where k is equals to 0 and n is equals to 1. Okay, so then we're effectively adding a cos pi x term. And if we do that and we have the right amplitude and we add it to a half, our approximation improves. So you can already see the oscillating nature coming through here with that first basic cos term, and it sort of captures the features of the absolute value thing, but not perfectly. It still disagrees over here at the spike and along the way over there. Let's add the next term. In other words, we had the next odd term, because remember the even terms are always 0. So if we add n equals to 3, okay, to the previous 2, our approximation improves. Okay. If we add n equals to 5, our approximation improves even more. N equals to 7, it improves even more. N equals to 9, it gets better. And then the approximation is already so good that if you start adding higher and higher terms, it actually makes very little difference. It just gets closer and closer to the actual graph, where our Fourier series is now almost exactly a periodic continuation of our initial absolute value function. Okay. So just let's examine this again in a slightly different manner that actually highlights what the coefficients are actually doing and where they actually are. So just reminder, we're approximating this function absolute value of x on the domain minus 1 to 1. There it is. Our Fourier series we expressed in the following way with L equals to 2, and our coefficients were a half, and then this was our general formula. Okay, and this is just another way of writing the same series that I did in the previous slide. So this is our Fourier series, and we can express it now with n simply summing over odd values rather than what I did with the k previously. And let us now look, as we build up a series approximation, what I'm going to do is I'm going to plot the Fourier coefficients, in other words, these Cn's that we can also use to characterize the function as we build up our approximation. So let's see what that happens. The first contribution in the series is simply a half. Okay, and so in Cn space, it's simply this dot, and that corresponds to this approximation of the function, so a pretty bad one. If we add the next Fourier coefficients, which are simply Cn1, which is equals to minus 2 over 1 squared plus pi squared, which evaluates to this value, the absolute value of Cn is simply sits over there, so it's 0.23. Okay, if we add the next functions, Cn2 is 0, and Cn3, we now again are going to have 3 squared, so we're dividing by 9, so the value gets much smaller, and in fact it is 0.0225, so it's that dot over there. And then we already have a very, very good approximation of the function. And then as we add the higher coefficients, C4 is 0, C5 is minus 0.0081. Okay, and we can do the same. C6 is 0, C7 is 0.042. Okay, and already our approximation is almost perfect, depending on how much accuracy you want. But we can go on, and we can approximate it even more, and we can add a higher order term, and you can see these terms are falling away pretty quickly. So it's a very, in this particular case, this thing is converges quite fast. Okay, and by the time we get to C13, C15 and C17, the function is tweaked a very little bit. So we can see that in some sense these coefficients are a representation of our original function, except that they contain the Fourier content of the function. And what we can see is that the major Fourier or frequency content of the function is the constant term, which is half, and then the fact that the thing is actually oscillating with a series, with a period 1. Okay, so typically in these plots that we're often going to be doing of the absolute value of the Fourier coefficients versus the number of the basis functions that they are multiplying, the low frequency information typically occurs here near 0, and it's going to change the large scale features of the function or capture the large scale features of the function. The high frequency information occurs out here around the corners. And one of the things that we're quite interested in when we look at these Fourier series, in other words, when we explore how well these series approximate our original function, and I'm just going to give the introduction here, is basically how rapidly these coefficients fall off. And we call that the convergence of the Fourier series. And it's basically answers the question, how fast does the absolute value of Cn decreases n approaches infinity? And for this particular example, the absolute value of Cn is just 2 over n squared pi squared, where n is odd. And so we would say that Cn decreases like 1 over n squared. So that's the convergence rate of this particular approximation. And as I mentioned earlier, Dirichlet, the major results about convergences of Fourier series were developed by Dirichlet after Fourier already used the technique, and we'll discuss a number of these features as we go on and study and look at more of these examples, because they also have important impacts when we start looking at images and, in fact, how we use the series to analyze images. Okay, the only thing I can say is that this particular rate that it falls off like 1 over n squared is typical of functions that are continuous, but that have discontinuous derivatives. So, for example, here our function that is just the absolute value function is continuous, but over here the derivative switches from -1 to 1. Okay, so because the slope is switching from negative to positive over here. Okay, so far I've just given you a very nice, or sort of a introduction to Fourier series with one example. What I will do in the next lecture is actually get you on speed with some of the programming. So a lot of because this is a very practical course, a lot of what we're going to be doing is actually manipulating data and getting the Fourier series, and later looking at images. And so I will be giving you an example of actually how I go about computing these graphs that I plotted for this particular example in Python, and how, in fact, to go about checking the analytic results I've gotten over here. But that will be given in a different video. Thank you very much.